Okay, so we're going to take a look at first ionization energy. The first thing we're going to look at is the definition. So when we're talking about first ionization energy, we're talking about the minimum amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. So let's put that right here. Great. And an example of an equation for first ionization energy might look something like this. So we might have sodium. Okay. So we might have sodium, and we're removing 1 electron from it, so we get sodium 1 plus and 1 electron. Okay, now some things that people tend to forget. You need to remember that the atoms need to be gaseous. So you need to remember to put the states, gas and gas, and you need to remember that this is for every 1 mole. So this is for 1 mole of sodium, and so therefore our units of ionization energy are usually in kilojoules per mole. Okay? So let's take a look at what happens in the periodic table as we go down a group and across a period. Okay? So as we go down a group, what happens is my ionization energy decreases. I need less energy to remove an electron from these gaseous elements as we go down a group. As we go across a period, my first ionization energy increases. I need more energy to remove an electron as we go from left to right. Okay, let's think about why this might be. Let's first start with down a group. So as we go down a group, as we saw in atomic radius, we have more occupied energy levels. So there's an increase in the number of energy shells. Okay, so again, if you forget, remember that we can number our periods. Elements in the first period have 1 occupied energy shell. Elements in the second have 2. Elements in the third have 3, etc., etc. Okay, so we have increasing number of shells, and therefore we have less attraction between the protons and neutrons. There's a greater distance. So we're going to do greater distance between the protons and the outermost electrons, which means that there's less attraction between the aforementioned protons and neutrons. Less attraction between those protons and neutrons means that it's easier to remove those electrons. So decreased attraction means it's easier to remove those outermost electrons. And so therefore, the energy required, aka the ionization energy, is less as we go down a group. Required. So down a group, we have more shells, more distance between the protons and the outermost electrons, less attractions, so they're easier to remove, and there's less energy required. Okay? Now let's talk about what happens as we go across a period. This one's a little bit tricky. So I'm going to write here. across a period, down a group. Okay, so as we go across a period, something that we call effective nuclear charge increases. So let's take a look at what that means. So we increase our Z effective, which is the symbol for effective nuclear charge. Okay, let's take a look at what that means by looking specifically at a period. So if we're to take a look at a period and choose a few elements, let's draw, for example, beryllium. So let's draw beryllium here. Then let's also draw nitrogen. And then let's also draw fluorine. Okay, so let's draw each of the subatomic particles within each of these elements. Beryllium has 4 protons. So we have 4 positively charged subatomic particles here, and it has 4 electrons. 1, 2, 3, 4. Now watch very carefully. These protons are pulling on the electrons. So they experience an electrostatic charge. However, these inner electrons are shielding that positive charge from the outer electrons. So these 2 electrons over here, 1, 2, are actually effectively canceling out the pull from 2 protons. So this one cancels out 1 proton, this one cancels out 1 proton. So the nuclear charge that is really available to pull these 2 electrons, or the effective nuclear charge, here is only 2. There are only 2 protons that are able to pull on those electrons. Conversely, let's take a look at nitrogen. So nitrogen is element number 7 on the periodic table, which means it has 7 protons. Okay, and it also has 7 electrons, 2 in the first energy level, 1s2, 2s2, and then we have 3 in the p sublevel, 2p1, 2p2, and 2p3. Okay, so overall I should have 7, and I do. Again, let's talk about effective nuclear charge. So this electron is shielding the other electrons from this positive charge, so it's canceling out the effect of one of those protons. This electron is also shielding the outer electrons, so it's canceling out this charge. So my overall effective protons that are able to pull in those electrons is 5. So here, my Z effective is 5. Okay? Moving on to fluorine, let's take a look at one last example. So fluorine has 9 protons and 9 electrons. So 1, 2, 1s2, 2s2, 2p5. Okay, so again, the shielding effect, where our inner electrons reduce the effect of our positively charged protons, is still in effect. So this electron cancels out this proton, this electron cancels out this proton, and my Z effective now is 7. So again, the number of protons in the nucleus that are able to pull on the outermost electrons increases as we go across a group. If the attraction increases, the distance between the nucleus and the outermost electrons decreases, and the amount of energy required to remove the electron that's in the outermost shell is more. Hopefully you can follow my logic. If not, I'll write it down. So we get an increase in Z effective. Perfect. An increase in Z effective means we have an increase in attraction between protons and electrons, specifically the electrons that are the furthest away. And an increase of attraction means that it's harder to remove. So we have a decreased ease of removal. Those electrons are more stuck to the nucleus as we go across the group because the effectiveness of the nucleus increases. And so therefore, the amount of energy required to remove an electron increases. And that's ionization energy. Okay, very quickly I have this little diagram that shows the energy levels. Just to demonstrate visually, we call this the ground state, so wherever my electron is when it's not excited, and we can label these different energy levels with numbers, and then eventually, if we keep going, we'll get to infinity, aka infinity. So E infinity, aka no longer attached to the atom. And ionization energy is the energy required, so say we have an electron here, to take that electron and move it all the way to infinite energy levels, aka completely off of my atom.